Hey you guys. So there's been a lot of confusion about the unit circle. Specifically, just trying to visualize exactly what it's about, and how it was designed and generated, and etc. And how in relation to these triangles, for instance, and the coordinate points and how to retrieve them, and etc. So let me just try to clarify some concepts. I'm not going to fill in the unit circle, but what I am going to do is just kind of give you a conventional outlook, a brief outlook on this, using properties from triangles that you've learned, including just the basic underlying characteristics of triangles, and then also properties such as the Pythagorean theorem, and how you use all this information to ascertain even further information to get for instance, points like on the unit circle itself. So let me show you. First of all, let's start off with the. I'm going to go quick. So sorry if if I'm too quick for you guys. So you can stop and record. I know stop and pause and take notes if you like. Hopefully this helps. First of all, we have two triangles. We have an isosceles triangle, and we also have a right triangle. Right. Okay, so we can go ahead and add 90-degree angle, right? Now, any the common characteristics of any triangle is that all the angles add up to 180, right? 180 degrees. So, in the isosceles triangle itself, we have this side equal this to this side to this side, so that all the sides are equal, and that also stands for the degree measurements. So, if this is all three of them equal to 180, then 180 divided by 3 angles would be 60 degrees each, right? Alright, and as well as this one, but I'm not going to write it in. I'm just going to leave it as is for now. Again, another triangle, the sum of all angles equals to 180 degrees, but we have 90 degrees angle, 90 degrees right here, so that means that we have 90 degrees left, and that divided by 2 is 45, so we have 45-degree angle, right? Cool. Dope. All right. One other thing is, again, I said on the isosceles triangle, all sides are equal. On the right triangle, well, we only have both of these sides are equal, but we also have a hypotenuse. Because once you've established a 90-degree angle, you've also established a hypotenuse, which is the side opposite the 90-degree angle. So this is the hypotenuse, right? Hypotenuse. And we're just going to give these values of 1. No, let me take that back. I'm going to give the hypotenuse a value of 1, right? And then say this is A, just for any generic variable. A doesn't mean anything, except it could be anything, really. And we've given these a value of 1, right? On the isosceles triangle. Okay, I'm going to stick to the isosceles for a little bit. I'm going to go ahead, cut it in half. And you'll see why in a second. Cut it in half, right? So what does that do if we cut it in half? Well, first of all, you got to understand that you've also cut the degree measurement in half. So this was 60 degrees originally, but now you're left with 30 degrees, right? We've also established a 90-degree angle. So this means that this side now is a hypotenuse, right? You see these emerging properties. And also, because this base was 1 total, well, now we're just left with 1/2, right? For these lengths, right? For half the length, and total is 1, right? Okay. Now, the reason why I did that is because we're only going to be using half the triangle. So what I'm going to do is do this. I'm going to kind of highlight this, if I could. Whoa, that's hard. That's bad. I'm sorry, you guys, but hey, you get the point. Anyways, we're only using half the triangle, right? And then we're going to further that, and we're going to go ahead and use the Pythagorean theorem on that. Why? Because you're going to get the length using the Pythagorean theorem. You're going to get the length of this side, and we'll call it B for now. B, right? Some people call it H, but I'm going to use it as B and designate it as B because you're going to see how it relates to the Pythagorean theorem. Pythagorean theorem is the sum of one side, or the sum of squares of both sides equals to the hypotenuse, or the third side squared, right? Or the square of the third side. the sum of squares of both sides, right, the base and height, equals to the hypotenuse squared. So we've already given the hypotenuse a value of 1, so I'm going to go ahead. Oh, and we also have a. We'll call 1/2 a. So this is the base, right? We have one side. We're just solving for this other side, this other length that we've kind of induced or put in ourselves or incorporated, you know? So we'll say one side is 1/2 and square it plus b squared, because that's what we're trying to solve for, is equal to c squared, which is just 1 squared, or 1, right? Remember, this is the hypotenuse. We can go ahead and solve for that. 1/4 plus b squared equals to 1, and then carrying on our proceeding, b squared equals to 3/4. B simply equals to √3/2. So b, our added length, is √3/2. Right? Cool. We can do the same with this triangle, except we're not cutting it in half. We're actually going to use it as is, as a whole. What are we going to do? Let's say, well, we have a squared. Remember, the hypotenuse is 1. So a squared plus a squared, right? Because both these lengths equals to 1 squared. Or 2a squared equals to 1. A squared equals to 1/2. Or simply a equals to 1/√2, right? And if you rationalize the denominator, √2/2. By the way, square root of a, one of my students was lost on this. A squared equals, so I'm taking it from this point. A squared equals to 1/2, and then if we're going to solve and isolate a, remember, we just take the opposite. We're going to square root. A equals to square root of 1/2, but the square root of 1 is simply just 1. So you have the square root of the 1/√2, and then we rationalize and get this guy right here. Another thing to add is that we don't use the minus because we're talking about length. Length is always positive. Okay, cool. So now we have that kind of settled, right? How does this work in relation to the unit circle? Well, you're just taking these triangles, well, half of this triangle and this triangle, and what you're doing is you're using both of them and you're orientating them around so that you can get certain degree measurements within the unit circle, and then also taking the lengths to verify your x and y values, right, for the specific sides. And on top of that, one other thing is that the hypotenuse now becomes the radius. So you set these triangles within, let me go back down, you set these triangles within the unit circle so that that the hypotenuse now assumes the position of the radius. And because we said that both circle and both triangles, the hypotenuse has always been 1, and that just makes the unit circle great to work with, right, with the hypotenuse or radius of 1. So the hypotenuse is, I mean, you even see a bigger emergent property. The hypotenuse of a triangle is now just the radius of the unit circle, which is really cool. So we can go ahead and say, let's give a, sorry if I lost you right there. These things are sometimes hard to explain. So again, if we take a 30-degree angle, right, we're just orientating and we're moving that triangle around. That looks like a 45, but that's supposed to be a 30-degree angle, right? 30-degree angle. And we said this is the hypotenuse, or 1, right? Well, if this is 1, I'm just going to draw like an imaginary side right there with the 90-degree angle. Well, then that now looks like this. Here's the 90-degree angle. Here's the radius, and here's the 30-degree angle, right? So we see the side opposite from a 30-degree angle is what? 1/2. So the side opposite from the 30-degree angle is simply 1/2. And the side adjacent to the 30-degree angle, or cosine, is √3/2, right? So this length here that you see, oops, no. This length right here, and this length now have their denoted values, right? 1/2 √3/2. Oh, sorry, no, xy. I always do that when in relation to the coordinate system, √3/2, right? Same thing with 60 degrees. So now we're just taking, oh, here's a 60-degree angle, by the way. Okay, but now we're just taking this same triangle and inverting it so we can get a 60-degree angle. I guess you can say positioned at the center, right? Or at the origin, right? So now we're gonna execute a 60-degree angle. Oh, God help us all. I have a really shaky hand. Oh, God. All right. So that's 60 degree, right? The total is 60 degrees. Since we've done that, now we have like that imaginary line, and we have a superimposed triangle. The side opposite the 30-degree angle is 1/2, right? So this length for this 30-degree angle, oh, and then this side is √3/2. So you just inverted it. So at this point on the arc of the perimeter of the unit circle, you now just have an inverted. You just now have inverted these points, right? Because the side opposite 30, which is x, is now 1/2, the shorter length, and √3/2 now is y. Now, where does a 45-degree come in? Well, just place it right in the middle. Let's get red. Okay, so let's go in red. So if I make a 45-degree angle, or execute a 45-degree angle, right, which is half of 90. This is a 90-degree angle from here to here. One quadrant is 90 degrees, so half of that, 45 degrees. Sorry for the mess, you guys. And remember, the 45-degree angle is the easiest because we said both sides are equal, right? So that means we have a hypotenuse of 1. This side is equal to this side. That means x is equal to y. Or we can also say √2/2. One side equals to √2/2. That means the other side is equal to √2/2. √2/2. So that means this point here, xy, is √2/2. Right? Now you just remember those points in relation to how they fit in the quadrant system, right? And know that this is a negative x, y value, right? This is negative x, negative y, and this is positive x, negative y. And you just go ahead and ascribe these particular negative signs to the respective labels as you go around the circle. And that's it. That's simply that. And that's the entire unit circle. I mean, there's more to learn, but hopefully that put into some clarification of what it's about. I'll describe more in the next videos. If you have any comments or anything, or questions, leave me, drop me an email. I'll feel free to reply or reply or answer any questions, or even if you have critique, that's great. Thanks.